everyone, welcome back to my channel, and today we are going to learn about stereoisomerism, the one which is considered as a bit tough, but you need to keep in mind few points, and I'm going to tell you what are those few points, and you are going to ace it. Let's move toward our topic, that is stereoisomerism. So stereoisomerism, as we discussed in the previous videos as well, that it would be related to our geometric isomerism, in other words. So in stereoisomerism we have the compounds which whose molecules have the same atoms bonded to each other but with different arrangement in the space, like you know very well it's a 3D structure, it's not a 2D structure as we make it on the table. So there are XYZ axes and we have to arrange them in a space. So sometimes the molecules move to the other direction when there is a spin in the bond. So maybe if they are facing, like if like two thumbs are facing each other and the fingers of space are facing each other. Now look over here, if we just change, if we twist it, what is going to happen? There comes a point when thumb is in front of the fingers, and this would change the arrangement of atoms in the space. So we are going to learn about this in our this video, and uh, first of all we are going to learn about the cis-trans isomerism. Cis-trans isomerism or geometric isomerism, in which there is different orientation in the space. Let's go to the example and why this happens actually. This happens in double bond. Keep in mind this cannot happen in the triple bond. Why? We'll learn it later, but this cannot happen in triple bond. It can happen only in the double bond because there are two different, you can say, the groups are attached to the carbon. Like carbon is making bonds with three, basically, further atoms. One is carbon and the other two, if they're groups or atom, whatever. Because the pi bond make it very easy to rotate, so we observe this in the alkenes most of the time. So here is an example, the cis isomers that have two single hydrogen atoms on the same side, while in trans one they will be present on the different sides or the opposite sides. So therefore, there are two different ways to construct the 2-butene. Let's look at how we can make it. For example, if we consider this as a single chain, now you can easily see this one has carbon number 1, carbon number 2, carbon number 3, and carbon number 4. So this would be named as butene. And where is the position of carbon double bond? It's at 2. So we name it 2-butene. Now, how can we change it? Now, if you're going to twist this one, as I've told you, consider one thumb and four fingers. When we're going to twist it, just look over here. Here, the hydrogen and hydrogen is in front of each other. They are in the same plane. They are in the same space. But when it is going to rotate, they are in different spaces. They are opposite to each other. Trans means across, so they are across each other, and here now it is called as trans, that is across. Now they are not present in a same plane, they are not facing each other, but they are present in the different ones. So this is how we make stereoisomers. So let's see what is the possibility of cis-trans isomers. So as we have discussed earlier, that when there is a double bond, only then there is more chances of stereoisomerism, or a ring. Ring means a benzene is present, or it's a cyclostructure, only then it would be present where the atoms can rotate. In addition, two carbons must have two different groups. Like if it would have all the hydrogens on its side, like if we observe over here, if it would be ethene, definitely it's not going to be the stereoisomer. Or if it's propene, it won't be stereoisomer because there should be it should be attached to two different groups. Then for example here, now look over here, it's A, B, and B. Now if we twist it, it will become AB and DA. Similarly, AB and BA here become AE or DB. So the stereoisomers are formed when a carbon is attached to different groups. Similar groups are not counted. Let's learn about its more properties. So if they have actually the different physical properties and some different chemical properties, because there are two different spaces now, they are present in different axes. So maybe when a reagent is present for the reaction might not occur because the atom that it is going to be reacted with may be present in another plane where there is no access. So sometimes their chemical properties differ as compared to the general group, as we have learned in homologous series that the properties are quite similar, but if there is a geometric isomer, then they might differ. So the physical and chemical properties are generally different, and they start with alkynes displayed structure isomer beginning with 1 butane or 2 butane. However, though there is no geometric isomers with alkynes. Why? Because the carbon is bonded to only one other group. There are not two other groups. So only one. If one is there, definitely they are not going to be a different position. They would be on the same position. So here are a few questions for you. You need to attempt it and you need to tell me how many isomers you would be able to draw, because you have to make 5 structural isomers for hexane. Let's see how many can you make. Do tell me in the comments, are you able to make the all the 5 structural isomers or not, or if you're able to make only 4, 3, 2. I hope that if you follow the general techniques, just change the carbon numbers, you'll be able to learn. Let's learn with this. I'm giving you hint for your answer. First of all, you have to try with the 6 carbon chain, then you have to try with 5 carbon chain, then you have to try with 4 carbon chain, and in the last you have to try with the 3 carbon chain. Mean make the other carbons the substitutes, not do not include them in the main chain. These carbon chains mean the main chain, the longest chain that you have selected. So by following these tips, you can easily make the isomers. It's your practice time. Do make them and tell me whether you will be able to do it or not. Till the next video. Bye bye.